Okay, so we've been looking at the relationship between the electric field and the magnetic field and the direction of propagation of the wave. So the cross product between the electric field and the magnetic field gives you a vector which is proportional to the vector whose direction is in the direction in which the wave is moving. So this right-hand rule gives you the direction in which the wave is traveling. So let's do some examples of this. Let's say we have the electric field. So the electric and magnetic fields are oscillating. They were sines or cosine functions. And let's say we have a wave that's traveling in one direction. This is a plane wave. So the electric field, let's say, is oscillating in the x direction. And the magnetic field oscillates in the y direction. Let's find the direction in which the wave is traveling. All we have to do is put our index and middle finger to represent electric field and magnetic field directions to get the direction in which the wave is traveling in. So the electric field is in the x direction. So if this is, say, x direction here, this is the y direction, and z is out of the page, we have that our index finger has to be this way, downwards along the page, and the middle finger has to be to the right because it's in the y direction, and therefore the wave is in, so S is in the plus z direction as a result of that. Let's say that we have an electric field that is part of an electromagnetic wave. So the electric field is oscillating, but it's pointing in the minus z direction. Of course, that oscillation, if it's a cosine function, there are times when it's pointing in the plus z direction. But when the electric field is pointing in the minus z direction, if let's say the wave is traveling in the plus x direction, then we can figure out by the right-hand rule what the direction of the magnetic field must be. And the answer is, well, let's put our fingers, again, let's do, the electric field needs to be in the minus z direction, so that's the index finger, the first vector here. It has to be this way now. So electric field is that way. Our constraint is on the direction in which the wave propagates, which is my thumb, but the thumb must be in the minus z direction, so I have to turn it around like that. And my thumb has to be into the page, and so B, the direction of the magnetic field, has to be in the plus y direction. Let's think of another case where we have the electric field of an electromagnetic wave. These are plane electromagnetic waves. This is pointing in plus z direction. Let's say that the wave is traveling in the plus x direction, and we want to find the plane. So we have a circular conducting loop, and we want to get the maximum EMF. So we want the max EMF to be generated in this loop. What's the orientation? In what plane should we place this? Well, the key here is that we want the magnetic field to go straight through the loop, one way or the other. And so we have to identify the direction of the magnetic field. So the electric field is in the z direction. That represents the index finger, so I have to point that out of the page. The direction of propagation of the wave, which is the thumb, has to be in the x direction. So that looks something like that. And so I see that the magnetic field is in the B is in minus y direction. So the plane that I want to place my loop in is going to be, here's the drawing, it's going to be an XZ plane. That's the plane in which it lies. So we'll call it the XZ plane, such that the magnetic field, which is in the minus y or plus y direction, will go straight through the loop area.